this occasion, I want to show you some of our recent results on the spectra of Schrödinger operators with point interactions. And this is part of the results that we have obtained with Professor Dr. Vladimir Rabinovich. In particular, we have the motivation to study such kind of singular potential because we can find some application in solid-state physics and in photonic crystals and so on. So we would like to show you not only the mathematical part, but also the numerical implementation of some of our results. Okay, so we begin considering that we have some kind of potential consisting of countable point interaction. That point interactions is a linear combination of Dirac potential and first derivative of Dirac potential. So we have a countable set of such point interaction, and they are located on the real axis at the points that we represent by y, j. So they are arranged in some way, and we can see that between a pair of such point interaction we have an interval. And this interval is larger than 0 and is not infinite. So we have an arrange of such intervals, and this is a kind of a linear graph, if you can think in that way. So the union of that segments produce that linear graph, and on this space we define the following Sobolev space and the space of continuous smooth functions with compact support. So these spaces are introduced in order to search for solution of the Schrödinger equation, and they are typical spaces that we are using. Of course, H2 is a Hilbert space. So we have here the Schrödinger operator that we are considering, in which the potential consists of a regular part and the singular part that consists of the point interactions, in which we have the strengths or intensities of such Dirac delta distributions, and this kind of potential is supported at the points that we set in previous slide. So we have here this kind of singular operator, and we can construct a self-adjoint extension consisting of only the regular part, but the point where the point interactions are supported, we have this kind of point conditions that are provided in a matrix form. So a domain as an unbounded operator in L2 is given by this function belonging to this Hilbert space, but also satisfying the point conditions. And we have some recent results that proves that if the potential is real value and if matrices are also real, then this operator is self-adjoint. So in a case of interest is when the yes. Oh, okay, the score, of course, yes. This is self-adjoint in L2 on the real line. Okay. So up to this point we have an arbitrary sequence of points distributed on the real line, but we can now assume that the point interactions are periodically distributed, and also we can assume that matrices are also periodic. And of course, a special case is when potential is also periodic. We have here some of the results that we have obtained. However, I would like to say that we have some results regarding the case when potential is not periodic and also when matrices are not periodic. So here we presented only this case in which sequence of point matrices and potential are periodic. And under this condition, we preserve self-adjointness of our operator. Okay, we have here a fundamental domain of the potential denoted by gamma sub 0, and we have here this interval that we know as the Brillouin zone, or unit cell in the reciprocal space. And in this fundamental domain, we have a set of points of discontinuities. Okay, and at this point, we assume that potential may have jumps, but the jumps are well defined. In this case, since we have a periodic potential and we have all the conditions of periodicity, the standard way to treat this kind of problem is by using the Floquet transform, which is a kind of Fourier transform. And here we have the Floquet transform, the inverse operation. And applying this Floquet transform to the spectral problem, we obtain this simpler, in some ways, some simpler spectral problem in which we have only an operator acting on the unit cell that we are studying. But not in the point of discontinuities in which we have a certain point interactions. So these operators are often called block Hamiltonian, and as an unbounded operator, this block Hamiltonian has this domain. Of course, we have this Hilbert space, we have this point interaction, but also we have these quasi-periodic conditions. And it follows that these block Hamiltonians have discrete spectra. And this spectra depends on this parameter theta that lives in the Brillouin zone. And this parameter theta is often called quasi-momentum. Okay, so we have here that each one of the operators have discrete spectra. So as we move theta in the Brillouin zone, the union of this spectra produces the spectra of our periodic operator. So since our spectra is composed by continuous functions, the images of this function under the Brillouin zone produces segments like this. So we have that the spectra of the periodic operator consists of the union of these segments. So we have a band gap structure. Okay, so in order to obtain the spectra, we have to solve this spectra of the block Hamiltonians. So we proceed in a simpler fashion by trying to find the solution of this problem that satisfies the point condition, but also the quasi-periodic condition. So we propose solutions given in this form by a linear combination of linearly independent solutions that satisfy these initial conditions. So on applying these quasi-periodic conditions, we obtain a homogeneous system of linear equations that possesses non-trivial solutions provided that this determinant equals 0. This gives the following dispersion equation. Okay, this is a rather well-known procedure. You can find it in, for instance, in very thin books. And we have here is just recalling how we can obtain the spectra of that periodic operator. So the spectra is given by those real numbers such that this function d is between this interval, where the function d is constructed by this pair of linearly independent solutions that we propose in the first case. So finding the spectra of this periodic operator relies on finding a pair of linearly independent solutions satisfying the appropriate boundary conditions. For this, we can have the well-known SPPS method, not only for calculating these solutions for arbitrary regular potential, okay, but also because it provides us with a numerical method for obtaining the spectra. So we have to find that pair of solutions, and we focus on the Schrödinger equation, not only the fundamental domain that we choose. Of course, we have that the equation is not counting the points where interactions are located. So we construct a solution as a constant piecewise continuous function, okay, in each of the intervals that is between our fundamental domain. So this is a rather standard question on how to construct that solution, and we can apply the conditions specified by the point interaction at the points of discontinuity to find the unknown coefficients. So each of the parts of this solution is constructed from a pair of linearly independent solutions, Phi1, Phi2, Phi1, Phi2, with the other index indicating the segment in which these solutions are considered. So each of these pairs also satisfy the following Cauchy conditions, and from this we construct monodromy matrices as follows. So on considering these matrices and the interaction specified by the matrices A, we construct this full matrix equation, which contains not only the information of the specific potential in each segment given by the monodromy matrices, but also has the information of the point interaction given at the points of discontinuity. So we have here this general solution for our differential equation. So recall that we need a pair of linearly independent solutions satisfying the conditions at the point 0. So from this condition we obtain finally the solutions given in terms of the matrix T, which is our full or global matrix, and in this sense the function D, which specifies the spectra, is given by these terms of the matrix. So in this case we have here a way to construct the spectra of this operator on the basis of constructing monodromy matrices and on the basis of the point interactions specified for the problem. Okay, so up to now we have to recall that there exist some cases in which we can obtain closed form solutions, or we can obtain solutions in terms of simple functions, and usually these are called solvable models. One of them is when the regular potential vanishes identically on the real axis. So we have here that in each of the segments, the solutions that satisfy the specified Cauchy condition are, of course, sine and cosine functions. So it is easy to obtain the monodromy matrices in this case, which have this simple form. And in this case, we can consider this very familiar periodic potential consisting of only Dirac delta distributions. In this case, we can see that we have between each of the interval one delta potential. So since all these delta potentials have the same intensity, all the matrices have the same structure as follows. So in this case, it is easy to obtain the matrix consisting of this periodic potential and obtain, of course, the dispersion equation for this problem. And this is, of course, the very famous Kronig-Penny model. Of course, in the paper of Kronig and Penny, they consider a potential as a pairwise constant potential, and in some moment they shrink the potential so that it remains the area under this potential, and this is of course one of the definitions in which Dirac delta is taught in universities. Of course, this gives exactly the same expression, and in this case, finding the spectral bands consists in finding the intersection of the lines 1 and -1 with this function d, with this plotted by this solid line blue. So in this case we have here the formation of the spectral bands. This is of course one of the classical topics in solid state physics related to how solids have a band spectra of energies. And this is of course a single model, but we can consider a related model in which instead of having Dirac delta potentials we have the first derivatives. And of course this is another kind of generalization of the Kronig-Penny model in which dispersion relation is given in this way. Of course these matrices specify the continuity of the first derivative, but a jump of magnitude beta of the wave function. This is something interesting. So in other cases in which we have no exact solution, of course it is always possible to obtain solutions by means of numerical methods. We have of course plenty of methods we can use, but we have at hand one method that provides us with exact solution. This is the SPPS method. So we apply the SPPS method to each of the segments, and for the method we need a particular solution of the Schrödinger equation in each of the segments. Okay, this particular solution must satisfy some smoothness condition, but we can say that for almost arbitrary potential we can obtain a regular solution that can be used for the method. And in each of the segments, a solution is constructed as a linear combination of this series, in which a spectral parameter takes the form of the power of this spectral parameter, and these functions are calculated by this recursive integration procedure. So up to now we can see that these functions are defined, but it seems that the potential is not considered for the calculation of this function. But the information on the potential is carried by the particular solution u sub 0. So all the information of the potential is given by these solutions, and from this solution we construct the formal powers that we have here. Moreover, the series have the very nice property of uniform convergence on each of the segments. So from these solutions we can construct monodromy matrices as follows. One matrix denoted by V, in which we have the power series, and the other matrix denoted by U, in which is constructed by the particular solutions that we need for each segment. Okay, so in this case the numerical method is given by considering in the previous series a truncated version. Of course this is an exact solution, but numerically we need to truncate the series up to some number of terms, and given the property of uniform convergence we can control on the error associated to the truncation. And if we use that truncated series, we substitute here and obtain an approximation of matrix V, and this gives us an approximation of monodromy matrix, and the procedures follow so on. So in this case we have here a single problem in which no point interactions are considered. In this case the singular potential is null, but we have a regular potential given by this kind of potential. Okay, this kind of potential very known for physicists, consisting of a kind of potential well, and in this case the transmission matrix, the matrix that we need, is given only for the only by these monodromy matrices, and we calculate the solutions by the SPPS method as usual, and obtain the function D given by this blue solid line and the intersection. So it seems that it is possible that no band are generated by this potential, but having this nice form of the monodromy matrices lead us to obtain the gaps between the spectra, which are given by numbers very small. So our method allows us to detect this gap and determine the edges of the bands. So in this case, this potential, it is possible to obtain closed form formulas for this, maybe in terms of geometric series, etc. It is possible to obtain in a closer form by means of power series of the spectral parameter. Okay, so in the end, this is
regarding the so here you some big crosses 1 minus 1.
Yes, it's for above and below the lines. But the plot, yes. But the plot seems that there are no crosses, okay? But instead we have some very narrow gaps in the spectrum. So in the following case, we have here a regular potential, of course given by another well-known potential, a sinusoidal, but also we have Dirac delta distributions. In this case, we have, for this example, one Dirac delta distribution in each of the fundamental domains, and we proceed with our technique and obtain the function D, and obtain the spectral bands for this potential. Okay, so in this case, for instance, we can obtain closed form formulas for the constant that we have here, and also it is possible to obtain, for instance, in terms of cylinder function for the potential given in this part. But we have here one way to obtain numerically more efficiently by means of power series.
The number of bands is infinite.
Of course, yes. Sorry. And in this case, the gaps tends to grow. And we have here that calculating the band H reduces to calculating certain polynomial roots, which is very, very nice, because we have plenty of method to calculate polynomial roots. So this is one of the advantages of this method, that calculating the spectral bands reduces to calculating polynomial roots. So another problem, and finally, here we have a potential, a regular potential given by this straight line, and we have two Dirac delta prime potentials in each of the interval. So in this case, of course, we apply the technique, calculate monodromy matrices, etc., and obtain the plot of the function defining the dispersion relation. So given the scale, we have here a very large scale. It is not possible to obtain the lines plus minus 1. So we indicated the bands by these strips. Okay, but we have the intersection of the blue solid line with the plus minus 1s, and this gives us the spectrum. So in this case, we have here one feature of this kind of potential, that as the energy, or in this case the spectral parameter, increases, bands tend to be very, very far from each other. So in this case, the gap tends to grow, and the spectral bands tends to reduce, to shrink, and these kind of potential are well known as Vanier stack ladders or delta prime scatterer, and the spectral properties of these scatterers can be obtained from this approach very easily. So I would like to thank you, and thank you very much.
Okay, please. Two short questions, please.
Well, the questions are short.
Okay.
The first one, what about the behavior of the solutions associated with the boundaries of the bands? Because in the usual problem, you find that these solutions fulfill oscillatory theories concerning the cells. Have you analyzed this property for your solutions here?
Yes, but that results do not fulfill. We have found that, for instance, the numbers of zeros that allow us to classify the function as odd or even, we do not have that result. It follows, for instance, if you have a singular potential with a delta or a delta prime, it is possible that solutions have no zeros. But also, for instance, the first solution, if you have only one delta, the first function have no zero, but it is the ground state. And also,
but I mean, in the periodic case, once you have these spectral bands, the solutions associated with the boundaries of the bands usually fulfill oscillation theorems concerning the cells of the solutions. Not the solutions in between, but the solutions in the border.
Okay, that we have not checked it.
The second one, when you are only yeah, no second one.
Enough. The second one, please go ahead.
You lost more time than mine. And I forgot that. The delta derivative you include alone in the sinusoidal potential is stronger singular than the conventional delta. And this means that this is not transparent. So that you find some difficulties in solving the problem because this strong singularity. How is it possible that you find solutions, as you show us, using only delta prime?
It is not too difficult. Delta prime traduces in matrix conditions that specify continuity of solution, continuity of first derivative and a jump in the solution. So from this, it is like in the case of the delta, that specifies continuity of the solutions, but a jump in the first derivative. So it is more or less the same case, and solutions are more or less straight.
And I advise to read the papers by using coworkers concerning these potencies.
Thank you.
Okay, thank you very much.